Yeah, so we're happy to have Jan talk about Pfaffian point processes for TASEP space.
Thank you. I'd like to thank Amor and the other organizers for this wonderful event. It's been a pleasure to be here. So this is going to be fairly introductory. I see a number of experts here in the audience who know quite a bit about this topic, but maybe not everyone. So I'm going to talk about the results of like two papers. One has been published by Gabali, myself, and Michael Wheeler. It's archive 2312. So I'll talk about this mostly today. It's about symmetric functions on 6-vertex model related to a half space. So that will be the topic of today. And then in preparation is a paper Mead, Daniel Remenick, myself and Michael. Which will really be about TASEP and the Pfaffian point process. So I wanted to point out some related literature to this. There's been the Pfaffian Schur process by Barakand, Corwin and Suidan, 2017. And there's a recent paper by Xinchen, which I should say, who's with Jeremy Quasto, I think. I'm not sure if he's still there. TASEP in half space, just last year, end of last year. And then there are several other papers. I should see Jimmy in the audience. So Jimmy, hey, of course, there's a paper on moments in half space as well, and several others. So just to mention those. So just maybe before I go into the details, a little summary of the outline of what I'd like to talk about. So TASEP we all know, right? There's particles maybe hopping to the right with rate 1, to the left with rate q, and they can enter on the left with rate alpha and exit with rate gamma. So this is what I call half space, and you should think of this as infinitely extended. So this is TASEP. More generally, I'll be focusing in lectures 2 and 3 mostly on the case q equals 0 and gamma equals 0. But that'll come today. So then if your initial coordinates, and let me see, the convention that I choose is that I take the nth particle closest to the left-hand side boundary and final coordinates like this, then you'd like to know the transition probability T starting in y and ending in x after time t. You want to compute that, and we'll do that using a discrete time 6-vertex model in stochastic gauge. So that's the content of this paper.
So you're assuming that the number of particles at the beginning and the end are the same?
No.
I mean, and in both cases.
Sorry.
Okay.
Thank you.
Sorry.
Yeah, no, thanks. Yeah, so using stochastic 6-vertex model in discrete time and then take a continuous time limit. And so many of you know this works, but maybe not everyone, so I'll go in detail through this. And then for the special case of TASEP, gamma to 0 and q to 0, we find that in this limit, Q and gamma to 0. And I'm going to also focus on empty initial conditions during most of the talk, because technically it's a lot easier, but we can say something for more arbitrary initial conditions. So X is going to be a sum over Pfaffians of some conditional L ensemble that was discussed by Alexei and Eric Rains a while ago. And the sum here is over Gelfand-Zetlin patterns, although a subset of Gelfand-Zetlin patterns that are sort of related to the final coordinates X. And this is a Pfaffian point process, and that means that all your correlations can be expressed in terms of Pfaffians ultimately, right? There may be sums over Pfaffian, so that's sort of the added bonus of this construction. So we'll go to this. So of course, this is in complete analogy with TASEP on the full line, where sort of a formula like this was derived by Tomohiro Sasamoto. So this is in relation to a determinantal point process. And that was based on a formula by Schütz, already in 97, I think, and then worked out by Sasamoto in 2005, and it was borrowed in Ferrari, Preyhofer, and Sasamoto in 2007, who sort of detailed this story. So we do this sort of similar thing for the half-space case, but there's some added complication. So I hope the outline is sort of clear. Yeah, maybe we should just start with lecture 1 then. So let's start with the 6 vertex model. 1 half space, and we'll start with sort of double row transfer matrices or operators. So maybe let me draw the picture first. I'm going to use these sort of pictures. And so I'm going to think of the top and bottom labeled by zeros and ones, denoting the particle configurations. So maybe I'll write these in terms of occupation variables. So eta I nu is just the indicator when I is in nu, and mu and nu are just sequences in n, so they determine coordinates of the particles, if you like, and then the etas are the occupation numbers. So etas are binary strings. And this sort of gives you the transition from a certain configuration mu to a new configuration nu, and then in between are 6 vertex configurations that do that, right? So there's some particle configurations. And maybe I'll put the 6 vertex model here because I do need it. So we think of a vertex that occurs in this orientation And I'm going to also add variables to it. So every line will carry a variable called the spectral parameter. And this will be some weight that depends on the ratio of those two parameters. And so what are the configurations that can occur? There are 6 of them. The empty. This will give weight 1. This will Q minus and over Z1. Okay, so these are the 6 vertex weight and stochastic A. So what I'm going to do is assign variables x and x inverse to the horizontal lines. But this line is pointing this way and the vertical lines are all pointing up. And some variables y, an infinite alphabet y for the vertical spaces. So we're going to compute this object. Often I will suppress the dependence on y. That will just be in the background. And this is going to be some operator x and so in the bulk, I'm going to use these 6 vertex configurations. So the matrix element of A will just be the particular configuration that you have and the corresponding Boltzmann weight, but I have to tell you what I get at the boundary. I'm glad there's a chair. I'm too tall for the bottom half of the blackboard. So at the boundary, you can have these weights. So it's readable. And h of z is some quadratic rational function. So maybe I should give it explicit as well. I can't go outside the box. So h of z is going to be AC minus z squared. Okay, so but these A and C parameters are related in some way, in a very simple way, to the alpha and gamma. Sometimes it's convenient to use alpha and gamma, sometimes more convenient to use A and C. So for those of you familiar with, say, theory of type B, Hollywood, or common polynomials, A and C are 2 of the boundary parameters, like A, B, C, D. Yeah.
So C in terms of X and Y is twice. C.
Z is the ratio, sorry, yeah. So Z, think of Z as the ratio Y over R. Yeah.
Which Y in that case? Which Y? So basically you're at the boundary.
Oh, sorry, yeah, this should be, okay. Let me just call this X.
X or Y?
X. This X. So this horizontal line depends on X. So this weight depends on X. Yeah, X.
All right. The limit, right, to get the TASEP. To set some of these parameters.
Yeah, we'll get there.
We get there later.
Yeah. So yeah, so like the discrete time evolution for ASAP will be stacking these objects on top of each other, and every one would have its own x. X is like a time variable. And then if I take a certain limit x close to 1, this will give me a continuous time evolution. But I want to stay discrete for now because it allows us to derive some nice properties that we then can use to construct a transition probability for TASEP rather than sort of using methods of algebraic Bayes ansatz rather than coordinate Bayes ansatz for the experts. That makes sense. Maybe also while I'm here, so these weights are chosen such that you have the next equation and also the reflection or boundary n vector equation, which is due to Sklejanin. And that says the following. I guess everyone here has seen this before. If I have 3 of these objects with this sort of orientation, then I can move the cross to the other side. That. And if this was dependent on y, and this on x1 and x2, then x1 and x2 in the dependence on this part of the picture will have changed wrong. So you can move the x's around if you have this property. And reflection, let me draw it like this. So we have this boundary weight depending on x1 and x2. Well, here the dependence of the boundary weight is swapped. Okay, so if you have those 2 equations and you have a certain graph, you can use these properties to move the dependence of these variables x and also the y's around. So in particular, this object will be symmetric in the y's because I can put a square at the bottom, commute it through, and then take it off with the right boundary conditions. You can then prove that this is symmetric in the y's. So if I stack 2 of these a's on top of each other, you can prove that they commute. So maybe put it as a little lemma that a of x1 and a of x2 commute. So just imagine, I'll do a picture with the second relation, which is a bit more interesting. I have 2 of these on top of each other, and you stick an R matrix sort of in between them in the center, and you pull it all the way to this side. And I do the same with the top 2 rows, pull an R matrix to that side, then I sort of get this picture on the left-hand side. I can flip it around and pull the R matrices back out. And after that process, the x's will have interchanged. So you will just prove that these 2 commute. So we think of these as commuting transfer matrices. And if you have commuting transfer matrices, like this is a family of commuting operators, so they can all be diagonalized together. So that's sort of the hallmark of integrability, if you like. Right? So that's an important property to have. Okay. So the next thing is that I want to So this was my A. I want to construct another semi-infinite operator, which now has a slightly different boundary condition. So rather than putting 0, 0 at the far end, so remember this is at infinity, I'm going to put 0, 1. So I have to be a little bit careful about convergence. If I have a 1 at the far end, I need an infinite amount of weights like this one here that have a 1 at the right-hand side. And so this particular convention doesn't work because I get then infinitely many powers of this weight, which will either diverge or go to 0. So I want to set this equal to 1. And I can just simply do that by rescaling all the weights. And let me put a dot on this top row here. And so the dotted weight is just equal to the normal weight times times a factor, a simple factor, which, well, it should just be the inverse of this, right? So 1 minus qz over 1 minus z. Okay, so the dotted weights are exactly the same multiplied by this function, scalar overall. So they don't actually influence all these properties here. They just make sure that this converges because there's infinitely many vertices here to the right that are of this form, and they all have weight 1.
Picture down in the reflection equation, should the boundary weights be x1 inverse then x2 inverse so that they match on the right hand side?
Yeah, this one here?
Yeah.
Thank you. Thanks.
Sorry.
You're kind of losing the stochasticity. You put that. It's no longer stochastic. When you multiply all the weights by some constant, they don't have one anymore. Here.
I don't need the stochasticity for these dotted weights. So the A will be my time evolution operator. So I need stochasticity for this operator. I don't need it for this one. So this is going to be a different operator. And the use of this operator will become clear. These become somehow the eigenfunctions of this operator here. That makes sense. So let me put I'll put a dot. Call this operator B dot of Z, where there's a variable Z running around. And there's a commutation relation between A and B dot. It says that AX BZ is equal to X minus QZ over X minus. So this Z is not the same as that. It just Z is just sort of an auxiliary variable. So there is this commutation relation between the A's and the B's. And I'd like to sort of give a sketch of the proof of that. So, so this represents A times B. And what I want to consider is a slightly more general object where I'm going to put some crosses at infinity, like that. So we have X and X inverse, Z inverse. So I'm just concatenating some R matrices on the right-hand side and summing over the two options that I have here and the two options that I have there. For every choice of lambda, this edge will be fixed. And then for every choice of lambda 2, that edge will be fixed as well. So let's consider this. And you can do this, say, for finite letters, and we want to take n to infinity. And if n goes to infinity, when n goes to infinity, because of the choice of weights, the weights that are not 1, we can make them less than 1 by some appropriate choice of the x and y variables. And so if n goes to infinity, anything that doesn't have a 1 here will have one of the dotted weights that is less than 1 and therefore be exponentially suppressed. Right? So in the limit n to infinity, this lambda 1 is actually forced to be a 1. And this lambda 2, for the same reason, is forced to be a 0, because for this set of weights, I can only have zeros infinitely far away. And then that forces, so this becomes 1, and forces this to 0 and that to 0. Right? And that is the configuration I want. This is again A times B. Right? But I can write it like this, because now I can use the Yang-Baxter and reflection equation, and I can pull this R matrix all the way up here, and this R matrix all the way here, and then end on the left-hand side with a configuration like this, and then switch it around, and then pull it back. And when I pull it back, this cross will have moved here. Okay, so we get something that looks like this. With a 0 and a 1. And now the sum again is over lambda and 2. Lambda 1 is again a sum. But for the same reason as before, these sums are actually, they freeze into the case where both lambda 1 and lambda 2 have to be 0 in the limit n to infinity. So this becomes 0. So the first picture, and then the dots. Sorry, I should have said the dots. The dots move now. They move to the line that has the 1 at the far end. Okay, so the first picture was equal to the second picture, which is now the operators have swapped turns, but you also have to now take care of the particular weights that these vertices had. And that if you do that in the right way, they account exactly for these factors here. Okay, so I hope that sort of clear that this is the type of recursion relations that you can find. So now I'm going to define two objects, G nu mu of x1 to x L, say. And this is going to be so I'm going to use like a physics bracket notation. So mu will be my bottom configuration. And then I'm going to stack these double row A operators. And then nu will be the top configuration. And let's say F mu Z1 Zn is the same thing, but now with the B dots.
It does commute with each other, right?
So the A's commute with each other, and the B's also commute with each other. So these are symmetric functions in their alphabets because of the commutation. G, so this G is like the discrete Markov generator, if you like. So this will ultimately be a time evolution operator, right? Think e to the t lambda, for those who work in continuous time. And this f will be like a off-shell beta ansatz state, for those who know what that means. But it's sort of the like a almost eigenfunction of these operators here. But they're useful to implement initial coordinates and final coordinates. So we'll have to use those. So one important quantity that these two symmetric functions satisfy, based on this commutation relation between one of them, is a skew Cauchy identity. Which is like, yeah, so I should say, I guess I said these nu and mu's are the coordinates of the particles, but they really are just partitions. They're ordered sets of integers. And so think of them as partitions. So then this would make sense. Summing over kappa over nu of the alphabet x, f kappa over nu. Right, so I'm just going to take a large product of these a's here and a large product of the b's and then move all the a's to the other side. Every time I do that, for every x and z, I get factors like this. So
Here, is mu supposed to be a subpartition of nu or a certain relation? I mean, you wrote it as if one was if there's an interlaced.
yeah, yes, so that mu has to be contained in nu.
Oh, because the particles always move to the left.
Yeah.
To the
To the
right.
right.
Well, particles always move to the right if you have horizontal lines pointing in both directions.
But it's suggestive of that, which will be important later on. So for now, maybe not necessarily. For TASEP, they will be. I will set that. There's certainly properties like if kappa is empty, nu has to be empty as well. But
Oh yeah, sure.
yeah. So this is just going to be products over z's in the alphabet of x in the alphabet x and z in the alphabet. Sorry, I should say z here. X my q z.
But then the left-hand side, maybe it should be g of z and f of x, not in this identity you're writing.
I haven't finished writing this out.
So it should be g of x still.
This is g of x.
Used to be b dot of z all the time. Oh, I'm sorry. Sorry, my
Sorry, I had a of x, right?
sorry.
And b of z. Yeah. And so now this becomes sum over lambda f mu lambda z nu slash lambda times. Okay, so I have some analog, some symmetric functions g and f that satisfy this q Cauchy identity, where this is really an infinite sum now, and this is a finite sum. This lambda needs to be contained in mu and nu. And you just get these products.
Okay, last one of the views should be a
Thank you. Yeah. Yeah. So there's a special case, if mu is the empty initial condition, then we have that f of empty, z really is only, so f consists of these b dot operators. So if my bottom state is completely empty with zeros, but a 1 needs to go out in infinity here, it needs to be created at the boundary. And so the only weight you get is this weight here at the boundary, and all the other weights are 1 by construction. So f empty is going to be the product in the alphabet z h of c. Okay, so if you have mu is empty in this relation, the right-hand side simplifies because this whole f is not there, it's just a product over h's. And we just have g of kappa being the transition probability to go from empty to some configuration kappa times f is this product of h's times g. Yeah. So I want to focus a bit on this empty initial state, because that is makes life a lot easier. And in this case, there's an alternative form for G, namely so instead of this stack of double row A operators sandwiched between an initial state and the final state nu, I claim that this partition function is the same as that stack as a partition function. So there's some f-basis argument to show that, which I won't do today. So you just have to believe me. So one way to prove that is, for example, you can use recursions in the y variables to show that. So if you set y to 1 over x, for example, for any of the x's, there's some freezing of some parameters because some of these Boltzmann weight become 0, like if the z is equal to 1, for example. And that's a way you can prove the identity. But the reason I'm showing this is that there's now this sort of special object, which is this triangle, which is a special feature of this half space construction. So in particular, the transition probability to go from an empty state to an empty state, which on the full line case is just trivial, here is not trivial because it just means that no particle net no particle has sort of entered the system, right? They could have entered in between. There's some ghost particles that say entered at T1, moved around in the system, and left again at T2.
Right. Why are there now like 2 alphabets for the G? Maybe I missed something. Like
Yeah. So.
Oh, I see.
So A of x, I was always suppressing these y's.
Thank you. Yeah, yeah. Okay.
Yeah, okay. So I have a stack of A that give me all the X's, and then every A depends on the infinite alphabet Y. Yeah. So I really don't want to. The Y's are just there as spectator variables, and as you know, often they can be used to prove things because they're very handy for proving recursion relations, etc. But at the end of the day, you want to set them equal to 1 for the application to TASEP. So this we call ZL, and this is really the partition function with all zeros. And point is that so a lot of the difficulties or the challenges with the half space case, the fully general half space, is that this object is not trivial. As the full line going from empty to empty is because you have particle conservation. This is a trivial object, but here you can have sort of ghost particles moving around, being created, but then disappearing again, right? And so the initial state is here and the final state is there. So it's a non-trivial object. And it took us a while to figure out, but this object is given by a Pfaffian. So in special cases, this was known, for example, in the case where the parameters A and C are infinite. In that case, the boundary K matrix becomes off-diagonal. This H goes to 1. And so I only have the off-diagonal cases. And this was a case that was considered by Cooperberg in the study of alternating sign matrices, some symmetry class of alternating sign matrices. So that is the case where you only have this second term. And that is a known Pfaffian. It actually factorizes in, and you can just analyze nudie asymptotics in a fairly straightforward manner. The fact that we have 2 terms here makes this a really nasty object to work with in full generality. So this, yeah. So after we found this, we learned that a group of Roger Berendt had done this independently in the context of alternating sign matrices. So I should mention that. And I forgot, I'm sorry, I forgot the other authors on that paper as well. So they did it independently.
Yeah, should I think of this as an analog of is again correct and determined?
Yeah.
And there is only a verification proof, or there is a conceptual reason why there is a fund?
Are you going to tell us how this is good or?
No, well, no, yeah, so no. Okay, so I was going to just, my comment was going to be the proof is by, so the answer is no, I don't have a conceptual understanding. Yeah, if I'm being honest, yeah. But so there are recursions like this, like in the, so, okay, maybe since this was mentioned, the so this case, the square case is the is again correct determinant for 6 vertex model with domain wall boundary condition. So this is very well known. This is a very nice determinant And in, you know, in some homogeneous limit, it factorizes very nicely. So it's a lot known about this. So this is the Pfaffian analog. As you can see, it's really just sort of taking the off diagonal of it. So it corresponds to some symmetry class of these configurations, if you like. But no, I honestly don't really know don't have a good understanding. And also this Pfaffian is really not as nice, nowhere near as nice as the domain wall, as the Isagen corp indeterminate. Yeah.
Wow. What a computer experience. Not an easy thing to guess.
So we did a lot of computer. Okay, so we have some tools, as you know. So there are some insights in expressing these things as sum over subsets. So we had a formula that was a sum over subsets. There are you know, there's there are formulas like this, right? The Pfaffian of A plus B is like a sum over subsets of the indices of A and B. The Pfaffian A Pfaff of the minor Pfaff. Don't want to write the details. So we had some formulas like this. But then to recognize that that actually comes from this was doing some computer experiments. And one day Sasha Gavali walks into my office and he sees my screen and he says, well, that's the Cooperberg Pfaffian. He just looks at some expressions like it's some computer screen full of polynomials and he recognizes it. Lots of X's and Q's and said, oh, I know that. And so we knew, so then we had a formula where we recognized this part as being the Pfaffian of this, which is the Cooperberg Pfaffian. And then the rest, I mean, this bit is easy. These are just some prefactors. So that's how it was found. By now we have more sophisticated methods because you can get these things if you have recursion. So you get the recursion relations by looking at the picture. Every time you, so maybe I should say a little bit about it. This local configuration can be either 0, 0 or 1, 1, right? Those two configurations. But if you set this XL equal to 1, then the zeros, well, one of them cannot occur. I have to, maybe I do the wrong one. Anyway, sorry. One of them cannot occur, and then you get a relation to something one size less. And so there are recursions that you can easily deduce from the pictures. Then once you have such a formula, you just need to prove that it satisfies the recursion as the same degree as this partition function. That's a fairly easy argument. But to get the formula is harder. But by now we understand it's related to shuffle algebras and things like that. So if you have recursions, you can quite often get to these type of formulas using shuffle algebras. So there is some glimpse of construction that some property like this needs to exist. That answers your.
Someone to look at different views.
In a paper, we write about this function can be expressed as a shuffle exponential. So I guess that's sort of and the same for this object. So it's like some shuffle exponential of Z1 plus Z2. Maybe, yeah. So the generating function of all of these objects. So if I know the cases L equals 1 and L equals 2, I can then shuffle it up, if you like. And then these sort of properties follow. But that's really all the best answer I can give. How am I doing? Yeah.
One question. But you said that you can relate. You talked about symmetry classes of the problem of the full.
Yeah.
But can you see that the Pfaffian goes into determinant there? by putting together these two pieces some way.
We haven't thought about doing that. Like really, this boundary here are these configurations, right? And they're sort of independent. These weights on the boundary is sort of independent from the bulk weight, so you have to find a way to combine them. So now we haven't really considered doing that. Yeah, but I assume you could do it. Yeah. Does everyone know what a Pfaffian is? I have it actually defined here, but I was assuming everyone knew what a Pfaffian is. Yeah, okay, I'll take that as a yes. So I'm going to leave it for a moment. If in my original problem, if both the top and bottom state or the initial and final state of TASEP are empty, then the Cauchy identity becomes sort of interesting. That these are no longer Q, but just summing over all partitions kappa of G and G of X. This is a whole alphabet. F of Z is going to be the usual sort of Cauchy type product for type B. So if X minus Z, but also 1 minus X times Z, and times the Pfaffian of X times Z. And I'm sort of highlighting this, that in the usual type of Cauchy identities you're used to, the right-hand side is just a simple product, right? Sum over sure functions, you get the product, sum over whole little whatever, get a product. In this case, we get the Pfaffian here, and that causes additional challenges. So that's why I want to sort of mention this here. Okay. Sorry, I was just too quick. Producing these. So I get this product from the commutation relation for between F and G that I had earlier, and then the last bit is another G, but now it's going to be G of empty, which is this Pfaffian.
Like Z of X, like ZL of X, right? Basically. Define.
Yeah, this is like Z of X, which is like G empty of X. Sorry, G empty of X, which is this Pfaffian. Yeah.
Q of X. Isn't there a Q in that there?
And this is an alphabet. So this is the Pfaffian of Q, X, I, X, J. Okay. But the X, I, X, J are taken out of the alphabet X. Okay. Yeah, sorry. Okay, so finally, I will now give explicit form for G empty to nu X. So really the partition function of this object here. And as a multiple contour integral, so G nu of X is some set of contour integrals. Maybe, so with dw, I just mean the product of dw1 up to dwn, and being the length size of the alphabet. Should have written that somewhere. So Lx is x1 up to xl, w equals w1 to wn. And y is just an infinite alphabet in y's, like a spectator alphabet. So these are
And n is the size of nu, right?
Yeah. 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 So I need to take n contraintegrals centered around x, all the xi's of this triangular object of size L plus n that has all the x's and all the inverses of w in it. Product of w in w and x in x of times product I less j a product I'll go through this slowly and that'll be the end for today. All right, so I'm claiming after evaluating all the contraintegrals, this expression will give you the partition function corresponding to these configurations here. And it will also be the discrete time evolution. So in full line objects or objects with periodic boundary conditions, you're used to these sort of multiple contraintegrals without this particular z factor, right? It's just a factorized integral, or potentially some over the symmetric group of factorized expressions. And but here we have so this is really starting from an empty initial state going to some state nu. We have this Pfaffian sitting inside here, and the Pfaffian depends both on the x parameters and the w's. So that's a complication. So this is where the limit gamma to 0, so gamma being the exit rate at the left-hand side boundary, is going to simplify, because for gamma to 0, the z will collapse completely and be equal to 1. Because for gamma to 0, you cannot have particles created at the boundary, and that will make this weight 0 and that weight 0. So it will really simplify things a lot. And then we can analyze, and you can see also that for Q to 0, things will simplify as well. This product here, for those working in continuous time, this product over the axis, think of x as time parameters. So this product here over the axis will become exponential, e to the lambda t, lambda being the eigenvalue of the transition matrix. So this will be the time dependence, and the rest will be like scattering conditions and boundary, and the new dependence sits here. And in this product, y less than y nu. Okay, so in view of the time, maybe I'll just say the proof of this, I'm not going to do this in detail, but the proof can be, if you think about the w's are centered around x, so that means that y nu I has poles around 1 over qx, j for every j, and so you prove this expression by recursion on those poles, which you can then relate to what happens in the picture. So
presumably it's a finite sum of residues, right?
Yeah.
Can you identify residues as some, configurations, sums over configurations in some way?
Yeah, so in the details of the proof, that's sort of what you do, but I think you're looking for some application of taking only some residues and as an observable, or yeah.
Or maybe, well, since you're mentioning recursion, maybe you just need single X, right? Or a single Y, sorry.
So the details are in the paper, but if you look at one particular pole, that some configurations are forced here, and you work through that, and that will then give you the recursions you need to prove that. So yeah, so it works like that. I think this is a good point to stop for today. Questions?